Good morning, everybody. So last time we started discussing about direct methods for optimal control. We saw that there are three classes of direct methods, shooting, collocation, and multiple shooting. And last time we managed to cover only the first two. So to quickly recap what we have seen, shooting boils down to this simple idea that we actually don't need to use as decision variables both the state and the control. We can only use the control because actually we can recover the state by integrating the dynamics, applying the control that we have as decision variable and knowing the initial state. Because typically in an optimal control problem, the initial state is fixed. So single shooting does exactly that. It only discretizes the control input trajectory, typically with a piecewise constant discretization. And then it recovers the state trajectory by numerical integration. So you don't need to have the dynamics as a constraint in the problem because the dynamics is automatically satisfied because you're integrating it to recover the state. For doing the numerical integration, we saw that there are different numerical schemes. The simplest one is explicit Euler, which is a first order method. So it's not very accurate. If you want to get higher accuracy for the same computational budget, you can use higher order method. Runge-Kutta methods are very well known and they all follow this scheme here. Some of them are explicit, others are implicit, and they are much more demanding in terms of computation because they require you to solve a system of nonlinear equation for every step of a numerical integration. They're rarely used in robotics. Here I gave you an example of a Runge-Kutta 4 method, the most popular one. And then we moved to collocation. Collocation follows, I would say, a simpler approach, which is to discretize both the state and the control trajectory. So you end up with more decision variables in your problem because you need to represent both trajectories. And in this case, you need also to have the dynamics as a constraint in your optimization problem. Otherwise, the state and the control could be completely unrelated. This is a simple way to discretizing the dynamics, which is to approximate the derivative of the state by finite differencing. You could use, even in this case, more sophisticated discretization schemes, which would be equivalent to using a higher order integration methods. But very often in robotics, we actually are quite satisfied with this simple approach. So what you end up with is a problem which has more variables, discretization of state and control, and also more constraints because you need to add these extra constraints with respect to single shooting, which represents the dynamics of the system. So at the first sight, it might appear like a lose-lose situation. There's more constraints, more variables, equal more computation time. So it's going to be slower. So why should we do that? Actually, it's not slower because we discussed that the problem is so-called sparse, which means that when you apply Newton's methods or some other gradient-based optimization scheme to this problem, you end up with a linear system of equations that you need to solve that are sparse. So the matrix that you need to invert is going to look something like that. So it's going to have some blocks around the diagonal, which are full of numbers, and everything else here and here, which is just zeros. So this system of equation is actually very efficient to solve because we have solvers that can exploit the fact that all these numbers are zeros, and so they don't contribute to the solution. And so if you use a so-called sparse solver, like the one that we are going to use in the lab sessions next week, we will see that actually you can solve this collocation formulation roughly in the same computation time that you can solve single shooting, or maybe even better. And then we need to move on to cover the last approach, which is multiple shooting. Multiple shooting is gonna feel like an in-between collocation and shooting. So the idea is, at a very high level, to discretize the control trajectory, like in single shooting. And then you also discretize the state, but only at some points in time. So you don't do a fine discretization of the state as you would do in collocation, but you only discretize the state every once in a while, which means that to recover the state trajectory in between these discretization points, you will need to use numerical integration. So you get a bit of both, a bit of collocation and a bit of single shooting, because you have some state variables like in collocation, but you need also to rely to a certain extent on numerical integration like in single shooting. So the discretization of the control is exactly the same as it was in single shooting. You typically use a piecewise constant discretization. So you assume that the control remains constant over a time step. And then you integrate numerically the dynamics in each interval to recover the state trajectory within that interval. So this is the usual differential equation that represents the dynamics of the system. And you integrate starting from the state variable that you have encoded as a decision variable in your optimization problem. Of course, you also need to integrate the running cost, but that you need to do it anyway. So I think that a sketch helps a lot to understand what's going on when you solve a problem using the multiple shooting approach. So what is going on under the hood is something like that. So when you start solving the problem, the solutions that you get before convergence is going to look a bit like this. So you have your piecewise constant control trajectory, as in single shooting or collocation. And then what's peculiar of multiple shooting is that your state trajectory is going to be piecewise continuous, because it's going to be for sure continuous inside the integration interval, because it's a result of a numerical integration of a differentiable dynamics. So it's going to be continuous. But then you're going to have discontinuities at the end of an interval and the beginning of the next one, because there the state is reset to the value of the decision variable. And during the optimization, you might have a so-called gap in the state trajectory. So this is somehow similar to what happens when you do collocation, because when you do collocation, since the state and the control, they are represented independently during the iteration before convergence, you might have discontinuities in the state trajectory, because the dynamics might be violated before convergence. Here it's exactly the same that's happening, but this discontinuity can only happen at the boundaries of your integration intervals. This is very different from what happens in single shooting, where since the complete state trajectory is recovered by numerical integration, the state trajectory is always continuous. You cannot have jumps when you do single shooting. So maybe we can stop for a second here to reason about this property of multiple shooting with respect to single shooting. So in single shooting, your state trajectory would be something like that. It would be continuous. It's impossible to have jumps. And at the first sight, that might seem like the best idea, right? The state trajectory should be continuous. So single shooting is the best, because it always gives me a continuous state trajectory. But actually, it turns out single shooting is the worst. Can you guess why? What could go wrong when you use the numerical integration in single shooting? It's always the same couple of things that can go wrong in a computer. In some sense, yes, but what kind of finite precision?
The fact that to calculate the integral, maybe if I have discretized too much of the values, I can accumulate errors of the positions.
Yes, you can accumulate error. That can happen also when you do collocation or multiple shooting, however. So that's not too problematic. There is another kind of issue which is always related to finite precision. So mathematically, there is nothing wrong with single shooting or collocations are completely equivalent mathematically. They should give you the same result. But when you implement this on a machine with a finite precision, then there is something that can go wrong with single shooting and instead does not go wrong with multiple shooting or collocation. So I think if even this drawing might help you understand what's going on. Look at what's happening with this state trajectory. Imagine continuing the integration. Where would this go?
Like further away from the actual state.
Yeah, it would diverge towards infinity. And imagine integrating this diverging behavior for a very long time, because maybe you have an horizon which lasts several seconds. What would happen on a machine?
Crash.
Not really crash. We can try it. So what happens? So 2 to the power of 10 is 1000. 2 to the power of 20, 2 to the power of 30. So what happens if I continue increasing this computation? It's pretty good at dealing with large numbers. Should crack at a certain point. It doesn't crack. Okay, apparently Python has no limits in how big a number it can deal with. Okay, I found the limit. And in this case, it gives me an error because it's Python. Actually, the problem was in the string conversion. Yeah, I don't know what Python is doing under the hood. But if you do that in a normal compiled language, what happens is that after a certain point, you get inf. The number becomes inf, which means infinite. You have a couple of special values in floating point operations, which, by the way, this was not a floating point, this was an integer operation. Maybe that's why it kept going for so long. You have none, not a number, which you typically get when you divide by 0. And you get inf, which is what you get when you overflow. So the problem that you might encounter when you do single shooting is exactly that. You might overflow. And that happens more easily than you may expect, especially in robotics. Can you guess why? There is a property of mechanical systems that makes this quite easy to happen.
Maybe I'm integrating all over positive values. So
No, it can also diverge in the negative direction.
Is it because of exponential? The function that I'm integrating is an exponential function, so it otherwise going to infinity very fast.
It's not really an exponential. So it's an exponential if your system dynamics is linear, and actually exponential could also go to 0.
Well, only if it's stable.
That's the key word.
Yeah, that's like robotic, only unstable.
Exactly, yeah. That's the property. So mechanical systems are typically unstable. And so when you integrate them with some meaningless control inputs, which is typically what you start with when you do trajectory optimization, it's very likely that it's going to diverge because it's an unstable system. So unless you do some like feedback control, it diverges by definition of unstable. And so it's very likely that if your horizon is sufficiently long, at the first iteration, or maybe after a few iterations, the numerical integration leads to infinite. And at that point, you're cooked. There's nothing you can do. I mean, your solver is not able to deal with infinite. Okay. And so it would typically stop with some error. And instead, if you do multiple shooting or collocation, that basically cannot happen. Well, in collocations, there is no numerical integration happening, so of course it cannot happen. But even in multiple shooting, if your integration intervals are sufficiently small, then sure, you're integrating an unstable system, but for a very short time step. So it cannot diverge to infinity. It will diverge, but only a little bit. And then you bring it back to a meaningful value. And iterating, the solver is actually going to be able to close this gap and make the trajectory continuous again, which is what you want in the end. But actually, during the iterations, it's good to be able to have discontinuities in the state trajectory because this prevents the divergence problem to infinity. Okay, so this is not very intuitive. It typically takes a while to grasp this concept, at least. It wasn't very intuitive for me when I started working with these tools. Any doubts, question? Okay.
So also in multiple shooting, I could have divergency.
Well, not really. I mean, unless you make this integration interval very long, but that's a bit against the spirit of multiple shooting. So the idea of multiple shooting is basically to get this benefit of collocation, but without going all the way to have a fine discretization of the state. So you can get the benefit, but without all the extra variables and constraints. And the multiple shooting NLP is going to look something like that. You have variables both for the state and the control input. You have your running cost, which is discretized, your terminal cost, depending only on the final state. And then for the constraints, you have initial conditions, you have the usual path constraints, and then you have this other constraint, which is peculiar of multiple shooting, which is called continuity constraint. And this is basically the constraint that tries to close the gap that you have at the jumps in the state trajectory. So this is the state variable. So the state at time step I plus 1 should be equal to the integration starting from the state at time step I, applying control yi until time ti plus 1. So this object here is basically the result of your numerical integration, and you would like this to be equal to this variable. So when you start solving the problem, this constraint is going to be violated. And then gradually during the iteration, the solver is going to try to satisfy it. But while this is going to be satisfied, also y is going to change, and it's going to become a stabilizing control trajectory. And so when the continuity gaps are closed, then y is going to be a meaningful control, and so your state trajectory is not going to diverge. So to summarize, here you can see a list of pros and cons of the different methods. So in single shootings, the main advantage is that we have a small problem, and we don't need to initialize the state trajectory. We need only to initialize the control trajectory, but this is not really a meaningful advantage, I would say. We can rely on off-the-shelf ODE solver for doing the numerical integration, which makes our life easier. You have plenty available online. But if you have a good initial guess for the state, you cannot really use it in single shooting. So if you kind of know what your state trajectory should look like, if you use single shooting, you cannot use that information because it only accepts an initialization for the control trajectory, because only the control is a variable of the problem. And the biggest problem is this, the one that we have just discussed. You have numerical issues for unstable systems, and most robots are unstable. So what helps with the stability of the system could be actually friction. So if your robot dynamics has lots of friction in it, this helps preventing the divergence, because friction prevents the robot from accelerating too much. But typically you cannot choose friction depending on the numerical properties that you would like to achieve. Friction is a physical phenomenon, so either you have it or you don't. And while it's good for numerical stability, it's not good for energy efficiency. So typically robot designers and manufacturers try to minimize friction. On the other side of the spectrum, we have collocation, which gives you a large problem, and yeah, it cannot adapt the time grid, which is something that you can do instead with single shooting, because you might have a numerical integration scheme that is adaptive, so it adapts the time grid. It doesn't use a fixed one, even though I don't think I've ever seen that in robotics, or very, very rarely. So it's not a big problem in practice. And the advantage is that the problem that you get is sparse. And so if you have a sparse solver, you can solve it pretty efficiently. It works well with unstable systems because you don't have the issue of divergence of the integration. And another advantage is that if you have a rough idea of what your state trajectory should look like, and in many cases you do in practice, you can use that information to initialize the solver with something that is meaningful. And that's going to help the solver, first of all, converging faster, and second, converging to a better solution. Because your problem typically is going to be non-convex, so it's going to have multiple local minima. And so if you provide a good initial guess, you're more likely to converge to a local minimum that is good for you. And multiple shooting basically is trying to get the benefits of both sides. So the problem has an average size in terms of number of variables and constraints, is sparser than the problem that you get with single shooting, but less sparse than the problem that you get with multiple shooting. And basically you have the advantages of collocation, of being able to handle unstable systems and initializing the state trajectory, while also possibly adapt the time grid with a numerical integration. And with that, we have concluded the part on direct methods. Do you have any question before we move on? Yeah.
I don't understand why the collocation cannot.
No, it's not that it doesn't have a time grid, that it cannot adapt the time grid. So the time grid is fixed at the beginning and it remains the same. In single shooting, I didn't show you, but there are some numerical integration schemes that can adapt the time step. Like a very famous one is ODE 45 in MATLAB. Maybe you have seen it. Those are a numerical integration schemes that can estimate the integration error that they are committing while they're integrating. And based on this estimate of the errors that they're committing, they can decide whether to use a larger or a smaller time step on the fly. That can be very useful in some cases because maybe you have dynamics that is very smooth in a certain time horizon, but then for a very brief moment it becomes very stiff, and so you need a very small time step but only for a short time horizon. So rather than using a very small time step all the way, you can just use a very large time step in the beginning when you can afford it, and then just go with a small time step for a very short period of time. So you get high accuracy without increasing a lot your computation time. Those are very special systems. We are not going to use those in our lab session, and I've rarely seen them used in robotics at all. You're welcome. Any other question? Okay, then we can move on. On Monday, we're going to have the first lab session on optimal control. So make sure you bring your own laptop, and we are going to implement single shooting and collocation so we can compare in practice how they behave on a trajectory optimization problem for a robot manipulator. Now, the next topic is going to be model predictive control, which is basically applying optimal control for reactive control of a robotic system. Because what we have seen so far for direct methods is basically how to compute a trajectory offline. So you have your robot, you know its initial state, you know the tasks that you would like the robot to perform. You formulate a cost function, all the constraints, the system dynamics, you set up your optimization problem using either single shooting, collocation, multiple shooting, you solve the problem, you get a trajectory, and that's it. That doesn't tell you how you can then execute this trajectory on the real system. And here you have different options. One option could be, well, I take that trajectory and I use it as a reference for a reactive control method, like task space inverse dynamics, which we have seen a couple of weeks ago. And that's actually what you're going to do in your first homework, which I guess you started looking at already. So that's exactly what we did there. We computed a reference trajectory for the center of mass of the humanoid robot. You have reference trajectories for the feet of the robot. And then you can use a reactive control method. In that case, it's a QP-based controller to track those reference trajectories. And that's fine as long as you don't have large variations with respect to the nominal system that you planned with. However, in many situations, you might need to have a control method that is a bit more powerful than a QP-based controller. Because we have seen that with a QP-based controller, there are many things that we cannot really do. So, for instance, you cannot modify the reference trajectory. The reference trajectory is given, and that's the trajectory you're going to try to track no matter what happens. So for instance, in the case of a humanoid robot walking, that method would be fine as long as the robot is not pushed. If you push the robot, then the reference trajectory that you have for its center of mass and its feet become meaningless, because the robot needs to change its center of mass trajectory and its feet trajectories to avoid falling down. So in that case, the methodology that you're going to apply in your assignment is not going to work. It's going to work only for small perturbations. But if you get a big push that allows you to move your foot to the side, for instance, then that's not going to be enough. So for situations like that one, or situations like maybe you want to do dynamic obstacle avoidance because your robot is moving in an environment where you have dynamic obstacles, which could be other robots or human beings that are moving in the environment. You cannot just plan the trajectory at time 0 and then execute blindly because the obstacles are moving. So you need to replan the trajectory in an interactive way. So the decomposition, trajectory optimization, and then trajectory tracking doesn't work in those scenarios. You need to re-optimize the trajectory every few milliseconds. So this idea of re-optimizing the trajectory inside your control loop is the key idea of model predictive control. So what model predictive control does is that it formulates an optimal control problem that looks like that. I've already written it down in discrete time. In this case, I'm assuming that I'm using collocation for discretizing the problem. So the state is discrete, the control is discrete. You have limits on your state variables, you have limits on your control variables, and you have a finite horizon n, of course, because that's the only optimal control problem that we can solve in general with a finite horizon. You solve the complete problem, you get the state trajectory, the control trajectory, but then instead of following the whole state and control trajectory, what you can do is that you can apply only the first control input, u0, and then at the next iteration of your control loop, you repeat the process. So basically, you throw away the rest of the control trajectory and the state trajectory, and at the next iteration, you just measure the state of your robot and you solve a new optimal control problem starting from this measured state. So basically, you re-optimize the trajectory depending on which state you actually reached. which may be different from the states that you predicted, because maybe there was a perturbation, or maybe your dynamics model that you're using for optimal control is not perfect. Or maybe you have sensor noise, so your state estimation is not perfect. So there is something that didn't go according to the plan. And if you do that, actually, it's very powerful, because every time you can be optimal with respect to your most updated information, your information regarding yourself, and also the information regarding the environment. Because if you have dynamic obstacles, then also this set here that defines the boundaries on the state can change depending on your state, on your perception of the environment. So if you know there is an obstacle there, you're gonna encode that in this set. You're gonna encode the fact that the robot cannot go there because there is an obstacle there. But at the next control loop, maybe the obstacle has moved, and so the definition of this set may be different. I think the key idea of MPC, which is the acronym we use for model predictive control, is pretty simple and intuitive. And actually, once you know how to solve an optimal control problem, you know already how to do MPC in a certain sense, because you're just solving an optimal control problem inside your control loop. So we haven't added anything yet to the theory of optimal control. We are just saying, okay, we're going to repeat this process many times instead of doing it just once. However, behind its simplicity, MPC hides many challenges, 3 challenges, which is why we need a complete lecture on it. It's not just ended with the first slide. I mean, you could just end it here and try to apply it, but you might encounter problems if you just apply it in the simple way I just explained. So if you want to make sure that you're really able to make it work in general, we need to take care of some issues that may arise with this methodology. And all the problems of MPC actually arise from this simple observation that the predicted trajectory is not going to be equal to the actual trajectory that the system the system performs. And this is surprisingly true even if you have a perfect model of the system and you have no perturbations, no sensor noise, nothing at all. Yeah, that's the right face, surprised. It is surprising because one would think, well, if everything went according to the plan, so my dynamics is perfect, my state estimation is perfect, I don't have any noise, any perturbation, I'm in a perfect simulation environment. Even in that case, the trajectory that you predict when you do the trajectory optimization is not going to be the same one that the system actually performs. It's going to be different. And if we stop for a moment to think about it, I think it will all make sense. So let's kind of simulate in our mind what happens when we do MPC. So we are at time step k. We are in this state xk. We solve an optimal control problem for an horizon n. So this is our time horizon. And we get this trajectory. So this is the optimal trajectory starting at this state. Then we apply the first control input and we reach this state, which is exactly the state that we predicted. No problem there. But then what happens is that at time step k+1, the time horizon shifts forward because it has a constant length. And now when we re-optimize for the optimal trajectory starting from this state, we don't get the same trajectory we had before. In general, we're going to get a different trajectory. And so when we apply the optimal control input computed at time k plus 1, we actually reach a state which is different from the one that we had predicted before.
But isn't this the whole point of MPC?
Yes, I'm not saying that this is wrong. I'm just saying that this is what happens. And it's not so intuitive.
But why is it happening like at all? Because I thought an optimal trajectory would be optimal from every position of my trajectory, so I shouldn't change it. Isn't that like the Bellman's principle?
Bellman's principle, we're going to get to that in a moment. Bellman principle only works if you have the same horizon.
Yes.
And in this case, the horizon is different because it shifts forward.
So
That's what makes it break.
Okay.
I'm going to tell you about Bellman principle in a few minutes. But first, I want you to digest this. So this is potentially, this is correct. It's what it's supposed to do. And it makes sense because the thing that was optimal when you were here may not be more optimal when you are here and you're looking further into the future. Because now you see what happens even after time step k plus 1 n. You see also what happens at time step k plus n plus 1. And so this might change what is the optimal thing to do now. So the reason why basically the system changes its mind along the way is that every time step that passes, the controller is able to look further into the future. And that new information that it acquires by looking further into the future may change what is the optimal thing to do in the present.
Isn't that how we get n plus 1? I mean, if I have a finite horizon, I just use it, all of it.
You mean instead of applying only the first control inputs, I could apply it until the end of the horizon?
I think if I have n time step horizon,
yeah,
that is the problem finished after n time steps?
Typically not. Typically the horizon that you use for your MPC is shorter than the horizon that you actually need for completing the task. So in general, no. It could be that it's the same, but most of the time is not the same. And the reason is simply computation time. So typically for performing a task, a robot requires a few seconds. And in MPC, we cannot afford an horizon that is so long. We typically have to work with horizons that are shorter than 1 second. And it's simply for computation time. Longer horizon, it means longer computation.
With the previous method, like collocation, we suppose that we land the whole trajectory, so the whole...
Because that was in an offline context. So your robot is there still, you optimize the trajectory, and after you're finished, you start executing it on the robot. In that case, you can use an horizon which is as long as you want, if you're willing to wait, because the robot is waiting that you're finished with the optimization before it starts moving. But with MPC, the optimization needs to happen inside the control loop, and the control loop needs to be fast to react to perturbations and sensor noise and whatever. So you cannot compute for seconds. You're convinced or not? Okay, so if this is the case, even without disturbances, perturbation, model errors, of course, it's going to be even worse in reality where you have disturbances, perturbations, and model errors. Okay. So why is this the source of the challenges? Well, first of all, this raises the feasibility issue. So the feasibility issue is the fact that even if when you start doing MPC, your optimal control problem is feasible, so it admits a solution, after a while, you might end up with a problem that is unfeasible. So there is no solution to the optimization problem that you're asking the solver to solve. And at that point, you're doomed. Because if there is no solution, of course, the solver cannot find one. And that's not only a problem of the solver. I mean, if there is no solution, it means that whatever your robot is going to do, it's going to violate some constraints. And typically constraints are related to physical limitations, like collision avoidance or joint limit satisfaction. And so it means that you're going to either collide with environments or with a human being, or you're going to hit a joint limit of the robot, which may break the robot, or you may need to exceed the torque limits to satisfy the other constraints. But if you exceed the torque limits, maybe you're going to burn a motor. So something bad is going to happen at that point. And it's too late to do anything about it. And then we have a second issue, which is stability. So there is nothing telling me that if I do MPC, my system is going to be stabilized. And that might seem counterintuitive because, I mean, you're always computing the optimal trajectory. So how can not be stabilizing? You're optimal. So you should also be stable. But again, because we have this problem that we are not actually following the predicted trajectory, we might be unstable. Because what could happen is that at each iteration of the optimization, we always optimize trajectories that diverge in the first step and then come back towards the origin. But since we only apply the first step of each trajectory, the overall behavior is a divergence. Okay, so that can happen in practice. It's not just a theoretical issue. I've seen it. And then we have a third challenge, which is much more practical, which is computation time. So typically solving an optimization problem is something that takes in the order of seconds. Here we need to do it in the order of milliseconds. Otherwise, it's not MPC. It's just trajectory optimization. So we need to figure out a mix of like smart techniques and efficient numerical implementation that allows us to achieve computation times that are typically below 10 milliseconds, or maybe even 50 milliseconds could be fine, depending on the task and the robot you want to control. So the rest of the lecture is basically addressing these three issues one after the other. And I'm going to tell you a bit what has been going on in the field to try to solve them. I would say they are still kind of open issues, so they're very difficult to overcome, but I'm going to show you what you can do about it. Any question before we move on? Okay. So before addressing any of this specific issue, let's start with a high-level observation. Let's talk about a hypothetical world in which we can solve MPC with an infinite horizon. So what if the horizon was infinite? Well, in that case, there is a crucial difference, which is that the horizon seen by the MPC, by the optimal control, it's always the same because it's infinite. It's infinitely long. So we don't have the same issue that we had before, that when I move from xk to xk plus 1, then I see something more that I didn't see before. Because if it's infinitely long, I always see everything. So in this case, what happens is that the predicted and the actual trajectories are the same, because I'm always optimizing over the same horizon. And at this point, things become much, much easier. So actually, this fact that when my horizon is infinitely long, I always get the same trajectory follows from the Bellman's optimality principle, which you mentioned before. So Bellman's optimality principle is one of the key principles in optimal control theory, which we're going to discuss more about when we start talking about dynamic programming and reinforcement learning in a couple of weeks. But very briefly, what Bellman's optimality principle says is that if you are given an optimal trajectory in discrete time, so going from time step 0 to time step n, if you take a sub trajectory of this optimal trajectory, so for instance, going from time step k to time step n, well, even this sub trajectory is optimal for an OCP with the horizon from k to n, starting from the state x star k. So said in simpler words, any sub trajectory of an optimal trajectory is optimal. So if you apply that to the MPC setting with an horizon that is infinitely long, we can see that the trajectory that we optimize at the first MPC iteration, which is going to be infinitely long and optimal for that horizon, if we take the sub trajectory starting at time step 1 and going until the end, well, that's also going to be optimal because of Bellman's optimality principle. And so the solver is basically always going to find the same trajectory. This is, of course, in the case without perturbations and modeling errors and anything. So that is very helpful, of course, if it was true. Because if we have an infinite horizon, then we can very easily solve the two problems of feasibility and stability. So for feasibility, it's quite obvious. Since predicted and actual trajectories are the same, the feasibility of the first optimal control problem implies feasibility of all the optimal control problems, because they always find the same solution. So if a solution exists at time 0, it always exists. Very easy. For stability, it's a bit more convoluted. You also need to take the assumption that your running cost satisfies this inequality. So your running cost must be lower bounded by the norm of the state multiplied by some positive scalar alpha. And if that's the case, then the fact that you have a finite cost at the first iteration implies that your MPC is stabilizing the system. I'm not giving you a proof of that, but I think it makes intuitive sense, because the only way you have a finite cost since you're summing an infinitely many terms like that, is if your state norm is going to 0, because you have an infinite sum of terms that are at least proportional to the norm of the state. So if the norm of the state didn't go to 0, you would diverge, and your cost would be infinite. Since your cost is finite, then it means that your state is going to 0, so your system is stable. So this is nice wishful thinking, but in practice, of course, we don't have an infinite horizon. Yes?
But given this definition of stability, in general, if the system is, I mean, probably is not, but it seems like if the system is feasible, then it will be stable. Because if it's feasible, I have a finite solution, and if I have a finite solution, then it is stable.
No, feasibility does not imply stability in general. You could have feasibility without stability. Because stability, so feasibility is just satisfying the constraints. So like for a mobile robot, it's not colliding with the environment, for instance. Stability is about remaining close to your target if you start close to it. So you could have an MPC controller that makes the system move far away from the target, but without ever colliding. So that would be feasible, but not stable.
But in that case, add produce a finite cost or not?
No, no, the cost would be infinite in that case.
So it's like stability.
So feasibility is necessary for stability, of course, because if you're not feasible, it doesn't even make sense to talk about stability. You're just crashing against a wall, so it doesn't matter. I mean, you cannot even talk about how close you are to the target because you crashed against the wall. But you can have feasibility without stability. Stability is about achieving the task in a certain sense. Feasibility is about not crashing. So the two things are I mean, feasibility does not imply stability. That's what I can say. You're not convinced?
No, but
Huh?
I get it.
You got it. I mean, we're going to talk about stability in a more precise manner in the following. So maybe it's going to become clearer then. So this is nice, but not very practical, because we are assuming that we have an infinite horizon, which of course cannot be the case in practice. But I wanted to guide you through this reasoning, because the ideas that we use for achieving stability and feasibility are kind of trying to imitate what an MPC would be like with an infinite horizon. Okay, so what we're going to do is that we're going to add a terminal cost and a terminal constraint. So a constraint on the terminal state and a cost on the terminal state of our horizon, to try to mimic what we would have if the horizon was infinitely long. So the terminal cost should represent the cost that we pay from that point in time until the very end of an infinite horizon. And the terminal constraint set should kind of do the same for the constraint. So satisfaction of this terminal constraint should ensure the possibility to satisfy the constraints from that point in time until the end of an infinite horizon. That's the idea. How we get there, I'm going to tell you after the break. So I'll see you back here in 10 minutes at 43. Okay. So this is our optimal control problem. And we've added to it a terminal cost and a terminal constraint. And the idea is, if we are able to choose wisely this terminal cost and this terminal constraint, we can fix the stability and the feasibility issues. The terminal cost is going to solve the feasibility issue, and the terminal constraint is going to solve the feasibility issue, and the terminal cost instead is there for solving the stability issue. So let's talk about, first of all, the problem of recursive feasibility, which in my opinion is the most important one in robotics. So the problem, the question we want to answer is the optimal control problem going to be feasible at all sampling times t? So first piece of information, if you have only constraints on the control inputs, then the problem is always going to be feasible. And if you think a moment about it, well, that's quite obvious. Your control inputs, you can choose them however you want. So if you don't have any constraints on the state, but only on the control inputs, there is always a solution, because you can just choose the control inputs that satisfy the constraints and you're done. For the states is different, because the state, you cannot really choose it. You choose the control inputs, and then the dynamics computes the next state. Okay, you cannot teletransport your robot from one point of the room to another. The state depends on the dynamics. So the problem arises when you have hard state constraints. But a piece of good news is that there is this theory called maximum output admissible set theory, which found out that actually you don't need an horizon that is infinitely long to guarantee feasibility. So even without the terminal constraint, there is a finite horizon that is sufficiently long so that you always have feasibility. We know that it exists. The problem is that there is no way to know how long it should be. So we know that there exists a value such that if your horizon is at least that long, you're good, but we don't know how long that is. And second issue, even if somehow we were able to figure out how long that should be, in practice, it very often might be too long. So maybe the horizon should be 1000, but you don't have enough computation power to work with an horizon of 1000. Because again, you're doing optimization inside the control loop, so you need it to be fast. But typically MPC is used with horizons that are quite short. Typically between 10 and 100 time steps. So this is reassuring that we don't need to go to infinite horizon, but still it's not very practically useful. So we need to go back to the idea of having a terminal set, terminal constraint. And here we can exploit this theorem, which says that if XF, which was our terminal constraint set, is control invariant, then the MPC is recursively feasible. Recursively feasible means if it's feasible at time step I, it's also feasible at time step I+1. And of course, if you apply this in a recursive way, you get feasibility forever. What does it mean that a set is control invariant? Because that's a key property we need to look into. So a set S is control invariant if for every state that belongs to S, it exists a control input U, feasible, such that the next state also belongs to S. So said in simple English, if you start in S, you can remain in S. So a control invariant set, you can think of it as a set that once you're inside the set, you can remain inside the set forever. It's possible to remain inside the set forever. That doesn't mean that you cannot leave the set. It's fine that you can leave it, but if you want, you can remain inside by using your control inputs. And when I say you, I mean you, the robot. So if we know a set that satisfies this property, then we can simply use it as a terminal constraint set in our MPC formulation. And we have this theorem that guarantees that the MPC is always going to remain feasible, which is very good. Why is that the case? So if we think a moment about it, I think it's pretty reasonable. So I'm going to give you a visual proof of this theorem, which I think works better than a 3-page of math proof. So let's suppose that we have a 2-dimensional state, x, 2 components, x0 and x1. So we can plot it in this 2D plot. And we know a set which is control invariant. It is this red circle, xf. And we start from an initial state x0, which is there. So at time 0, we call our MPC solver, which computes an optimal trajectory, which may be something like that. So this is x1 predicted at time step 0. This is x2 predicted at time step 0, x3, x4, and x5. So the terminal state of our predicted trajectory must be inside the terminal constraint set, which is xf. Now, since we are doing MPC, we are going to execute the first step of this trajectory, and we are going to reach x1, which is, in the nominal case, is going to be equal to the prediction. And at this point, we need to re-optimize. So why can we be sure that this new problem, starting from x1, admits a solution?
X5, which is the optimal, and I'd say is control invariant, so like it's going to lead into the
So x5 is inside the control invariant set, and that tells me what?
If I would follow my trajectory from x that I predict 0, I would get into the control invariant in that set, and then feasible and stable.
Well, stable, we cannot say anything about it yet. I mean, the trajectory until x5 is feasible by definition because it's a solution of my OCP. But then here I need to say something more. I need to say that I can also compute basically a value x6 that is feasible.
Yeah, I mean, like once you're inside the control invariant
Set.
You're not gonna leave, are you?
It's not that you're not gonna leave, it's that you can not leave. It's a possibility, is not a constriction. Okay, but yeah, that's exactly the property we are going to exploit. So once we are inside the control invariant set, we can remain inside. It means that starting from x5, there is a control input that allows me to move to a next state, which is always inside xf. So I can guarantee that starting from x1, a solution exists, because if I'm in x1, I can simply follow the same trajectory that I had predicted before, reach x5, and then I know that from x5, I can do something such that I remain inside xf. So the trajectory from x1 to x5 is feasible because it was the solution of the previous control of the previous MPC. And then x6 predicted at time 1 is feasible because my set xf is control invariant. Of course, xf should be feasible, should be a subset of the feasible set.
I calculate that in the first place. It's nice that it's there, but like how do I know at what point inside my feasible set is that?
So xf is going to be represented by a set of inequality constraints typically. So you just have to encode these inequality constraints in your problem. The real question is, how do I compute a control invariant set in general for a dynamical system? That's what we're going to discuss for the rest of the lecture.
It's not clear to me how the MPC calculates the same trajectory.
So yeah, very important point. I'm just showing that a solution exists. I'm not saying that this is the optimal solution. Actually, in general, this is not the optimal solution. But for feasibility, we don't care about optimality. Feasibility is only about the existence of at least one solution. Okay, this is not in general going to be the optimal solution because in general, we know that the prediction changes from one iteration to the next. So probably what the MPC solver is going to find starting from x1 is not going to be this blue trajectory that I just drawn. It's going to be something different, but I don't care. I only wanted to prove that a solution exists.
So it's like if on the first step, on the first prediction, I get into the feasible area, then even if I have some different prediction, I just throw them away, I follow the first, and then I have a solution.
I'm not sure I get the question, sorry. So what would typically happen is that when you're solving your MPC problem at time step 1, you could use this trajectory here as initial guess for looking for a solution. But then the solver can modify it. However, here we are not at all entering into the discussion of how a solution is found. Here the discussion is more high level, it's at a mathematical level, and we are trying to answer the question, does a solution exist? Then how to find it is a different story. So at this moment, I think you shouldn't worry about how to find it, because first we need to answer the question, does a solution exist? And then if the answer is yes, then we can discuss, okay, how do we find it?
I mean, I could just disprove it just if on the first horizon I end up in the feasible step.
In the control invariant set, not feasible, control invariant.
That is XF.
XF,
then,
yeah.
I'm done.
Then I know that a solution will always exist to my MPC problem.
And I can reach it.
It doesn't tell me that my solver is going to be able to find such a solution. That's a different story. A very relevant one, but a different story. So here we are only guaranteeing that a solution exists, which is of course a necessary condition for answering your second question, which is my solver going to find it? Because if one doesn't exist, then of course the solver cannot find it. Discussing how the solver can find a solution, well, we don't have any guarantee on that. We can just hope that if a solution exists, then the solver is sufficiently good to find it. That's a hope more than a guarantee. It's very hard to guarantee that if a solution exists, the solver can find it. I mean, we will need to add lots of assumptions on the kind of, like, if your dynamics is linear, sure. In that case, you can give pretty strong guarantees on the solver. But in general, when you have a non-convex problem, it's very hard to give guarantees on the ability of the solver to find a solution. In practice, however, it works quite well. Okay. An observation. Of course, this guarantee is under the assumption that you have perfect model, perfect state knowledge, no disturbances, no perturbations. Everything is ideal. Because if everything is not ideal, then of course, all this demonstration breaks down. You can generalize this concept to the robust setting. So assuming that your knowledge of the system state and the system dynamics is imperfect, but you have some bounds on your modeling errors, your state estimation errors, and so on and so forth. And so you can generalize this to like robust control invariance. It works. It just adds complexity on top of this. So I'm not going to show it to you. But the key idea remains the same. So let's now talk instead about how do we compute a control invariant set, because that seems to be the bottleneck. If I can compute a control invariant set, then basically I solved my recursive feasibility problems. So let's start with an example of a very simple control invariant set. Let's consider a robot manipulator. If you consider the set of all the states with zero velocity, so all the states where the robot is still, then that set is control invariant in general. In particular, is control invariant if your robot is able to compensate for gravity torques. And probably all robot manipulators, all serious robot manipulators are able to compensate for gravity. It means that the robot is able to stand still in this configuration where gravity torque is maximized. So this would be the definition of the set. And the fact that this is control invariant, I think is quite obvious. But if your robot is able to compensate for gravity, then every time it is still, so with zero velocity, then it's able to remain still in that configuration. So the set is control invariant because you can remain inside the set. Actually, you can remain exactly at the state where you're at. So this could be an example of a very simple control invariant set that you can use for guaranteeing recursive feasibility of your MPC problem. However, I would say that this is not a very good control invariant set to use. So you can use it. We are going to use it in the lab session. However, it comes with some limitations. Can you think of any? So what does it mean that you have to reach such a set by the end of your horizon? It means that at the end of your horizon, your velocity should be zero. That's basically what it is. You're saying that at the end of the horizon, your velocity should be zero. What does it tell you about your velocity at the beginning of the horizon? It's limiting your velocity at the beginning of the horizon. Because if by the end of the horizon, your velocity should be zero, at the beginning of the horizon, unless your horizon is very large, at the beginning of your horizon, your velocity cannot be very large. Because if your horizon is, I don't know, half a second, it means that your current velocity should allow you to stop in half a second. So you cannot be moving very fast now if in half a second you need to be with zero velocity. Because your deceleration capabilities are limited by your torque limits at the motors. So it means that basically you can never move very fast. Yeah. So having this set as a terminal constraint set means that at the end of your horizon, your velocity should be zero. And if your velocity should be zero at the end, it means that at the beginning of your horizon, so right now, it cannot be very large. Because otherwise you don't have enough time to decelerate from your current velocity to zero velocity. So if you use this terminal set, your robot is never going to move fast. Or to be more precise, you need a very long horizon for allowing your robot to move fast. So it's going to be a compromise between horizon length and speed of motion. And typically the horizon length, you cannot increase it too much because computation time then grows. And so you're just going to be willing to accept that your robot is going to move slowly. Which makes a lot of also intuitive sense. I mean, this is a way to guarantee feasibility, so to guarantee safety. And moving slowly, of course, makes it easier. So depending on the applications, this could be sufficiently good if you don't care about moving fast. But if your application requires the robot to move fast, because moving fast is typically good for robotics application, you want to maximize productivity, so you need to move fast, then this is not a good choice for your terminal constraint set. So we will need to do something a bit more complicated. Unfortunately, in general, computing a control invariant set is very difficult. So there is no easy solution to do that. the example we just saw is a specific example of a set of equilibria, so of states in which the system can remain. But a better choice would be instead to rely on the so-called backward reachable set of the equilibria. So what is a backward reachable set? Is a set of states starting from which you can reach a given set. So let's take this set here as our target set. So the set of fixed positions, fixed configurations. The backward reachable set of S would be all the states starting from which I can stop within a given time window. Okay. This is also an example of a control invariant set. Why? Well, we can reason a bit about it. So if you know that from the current state, you can come to a stop within a given horizon, let's say 1 second, then can you remain inside this set forever? Well, yes, because you can stop in 1 second and then you can remain still forever. So you remain inside the set forever. And this backward reachable set is going to be bigger than S. Because all the states that are in S, of course, they also belong to the backward reachable set. Because if you are still, well, you can reach this set, the set of still configurations in 1 second, yeah, because you can just remain still for 1 second and you're inside the set. But there are also states that are not with zero velocity, that are in motion, from which you can stop in 1 second by decelerating. Okay. So just to give you a drawing, which maybe helps. So let's take a simple one-dimensional system. So on the x-axis, we have the configuration. On the y-axis, we have the velocity. Let's suppose we have some limits. So this is Q min. This is Q max. Then the set S would be simply given by this line here. So that's the set of zero velocity states. It's simply a line in this case. And then if we compute the backward reachable set, it could be something like imagine this set here. This would be the backward reachable set of S. So why this could be the shape of the backward reachable set of S? Because from any state inside this purple set, like take for instance this state here, you can reach the blue set within 1 second. So for instance, with this trajectory here, or if you start here, you can reach it with this trajectory here. If you start there, you can reach it with this trajectory. You can also start in the middle. If you start in the middle, you're going to reach it faster. If you're at the boundaries, you're going to reach it using the whole horizon that you have been given, which was in my example 1 second. Why instead, let me change color. Why is this state here is not within the purple set? Well, because from this state here, even if you decelerate, you're gonna stop there. So you haven't reached S in the given time window. And if instead you start here, for instance, what happens is that you just hit the joint limit. So your trajectory stops there, hitting the joint limit, so is not part of the backward reachable set of S. Because of course, when we talk about backward reachable sets, so the ability of reaching a set, it goes without saying that while we are reaching the set, we are not allowed to violate the constraints of the system. We should reach it remaining feasible. Otherwise, this would be fine because you could go outside your limits and then come back like that. But that violates the constraints of the robot, so that's not acceptable. So backward reachable sets could be exploited as a better choice for control invariant sets rather than simply the set of equilibria. However, even computing a backward reachable set is not trivial. I'm going to describe how you can compute one using an approximation method, basically. So what we can exploit is that while we cannot compute the whole backward reachable set, it's very easy for us to check whether a given state belongs to that set. This is how I'm representing the backward reachable sets. I'm using this B for backward. This is the set that I have to reach. And N is the number of time steps I am given to reach the target set. So this is actually called N-step backward reachable set because I have N steps to reach something. So I was telling it's very easy given a state to check whether that state belongs to that set or not, because I can simply solve an optimal control problem starting from that state, trying to reach the state, the set S in an horizon N. If I find a solution to that problem, then it means that yes, the given state belongs to the backward reachable set. If a solution does not exist, then it means that the given state does not belong to the backward reachable set. So it's a bit computationally expensive because I need to solve an optimization problem to answer this question, but I can do it. It's doable, just to check if one state belongs to the set or not. So I can use this method basically as an oracle, and I can simply sample states randomly in the state space and call the oracle to give me a label for each state that I sample. So if the state belongs to the set, I put a positive label. If the state does not belong to the set, I put a negative label. And I can sample many states. And then I can train a classifier using a neural network, for instance, to try to distinguish these two classes of states, the states that belong to the set from the states that don't belong to the set. And of course, it's going to be an approximation of the set. It's not going to be the real set, but that's the best I can do in this case. So this is the Oracle optimization problem. It's an optimization problem without cost function because there is nothing I need to optimize. I need just to find a state and a control trajectory such that I start from the given initial state, x bar, and my final state is an equilibrium. So if xn is equal to xn plus 1, then it means that I am at an equilibrium because the state remains the same for one time step. It's a different way of representing that xn belongs to the set of equilibria. In the case of a robot manipulator, actually, I could also replace that with something even simpler, which could be simply that q dot at time step n is equal to 0. Because the only way that my state can be the same for two successive time steps is if my velocity was 0 at the first time step. And then, of course, along the trajectory, I need to satisfy the dynamics of the system and all the state and control constraints. And basically, this slide is just saying what I just described. So I use a function approximation technique to learn an approximate representation of this backward reachable set from examples. And to build the data set, I repeat the following steps. I sample a state randomly. I check that the state is feasible, because if it's not feasible, well, I shouldn't even bother. If the state is feasible, if the state is not feasible, well, it's not going to belong to my control invariant set. So I add the point x0, where 0 is the label for points that don't belong to the set. Otherwise, I try to solve the optimal control problem. If a solution has been found, then I add the state with a positive label to the data set. Otherwise, I add the state with a negative label to the data set. And then once I add my data set containing this pairs state label, I train a classifier using a neural network to predict the label given the state. So like there are classifiers for identifying whether an image contains a cat or a dog. Well, you can use also classifier for identifying whether a state belongs to a set or not. It's the same principle mathematically. Once you have the classifier which has been trained, you can actually use the neural network as a terminal constraint in your MPC problem. That's actually how we achieve recursive feasibility in nonlinear MPC and robotics. We have to go through this kind of function approximation approaches. Of course, it's not an exact method because the moment you introduce a function approximation technique, well, you're going to have approximation errors by definition. But it's much better than not doing it. Because even if it's an approximate set, well, it works better than having no set at all. So that's everything I wanted to tell you about recursive feasibility. On Monday, we are gonna put theory aside for a moment. We're gonna instead start implementing optimal control problems with single shooting and collocation using Casadi. And then on Friday, we're gonna come back to the theory, and we're gonna discuss the stability and computation time problems of MPC. So see you on Monday.